So good morning to all, and welcome to the Nobel Laureate Lecture Series organized by Bhaktivedanta Institute, Kolkata. I'm Dr. Roshan Tiwari, a trained experimental physicist and quantum physics researcher at Bhaktivedanta Institute, your host for today. It gives me really immense pleasure to warmly welcome you to this very special and highly anticipated lecture by the renowned Nobel Laureate, Professor Carl Wieman. We are truly privileged to have him with us today. Professor Wieman will be speaking on a very interesting topic, taking a scientific approach to science and engineering education. A topic that promises to inspire and reshape the way we think about teaching and learning in this 21st century. The event is being organized as a part of a Golden Jubilee celebration of Bhaktivedanta Institute, marking 50 years of dedicated and selfless service to humanity, guided by the values of knowledge, integrity, and compassion. The event is being conducted in association with the various branches of Bhaktivedanta Institute, like Algadda, Bangalore, Bhubaneswar, Hyderabad, NCR Delhi, and Vijayawada. We would like to express our gratitude to our knowledge partners, Dr. T.D. Singh Quest Club at IIC Bangalore, Jigyasa Science Consciousness Inner Quest group from IIT Bhubaneswar, and several esteemed universities and institutions such as Soya University Bhubaneswar, NRI College Vijayawada, Government PG College Ranikhet, Aditya Degree College Vijayawada, School of Planning and Architecture Vijayawada, PB Siddhartha College of Arts and Science Vijayawada, Aditya Degree College. So these are some of the institutions. We also like to give special thanks to all the educational institutions whose support have helped us to make this event possible. Now, I would like to invite Brajlika Devi, Sulochana Devi, and Prem Abhinavani Devi to kindly invoke the divine blessings.
Yeah. Okay. Govindam Adi Purusham Tamaham Bhajami. Govindam Adi Purusham Tamaham Bhajami. Govindam Adi Purusham Tamaham Bhajami. Vedam Kvanantam Aravinda Dalayaksham Varahavatam Samasritam Buddha Sundarangam Kandarbhakoti Kamaniya Vishesha Shubham Govindam Adipurusham Tamaham Bhajami. Govindam Adipurusham Tamaham Bhajami. Govindam Adipurusham Tamaham Bhajami. Angani Yasha Sakalin Driyavritimanti Pashyanti Panti Kalyanti Shiram Jaganti Ananda Chinmaya Sadhu Jala Vigrahasya Govindam Adipurusham Tamaham Bhajami. Govindam Adipurusham Tamaham Bhajami. Govindam Adipurusham Tamaham Bhajami Govindam Adipurusham Tamaham Bhajami Govindam Adipurusham Tamaham Bhajami.
Yeah, thank you. Thank you very much for this beautiful invocation. So now let us watch a very exciting video introducing Professor Carl Wieman.
Join us for an inspiring Nobel Laureate lecture titled Taking a Scientific Approach to Science and Engineering Education by Professor Carl Wieman, one of the great minds who reshaped modern physics and science education. Professor Wieman created the first Bose-Einstein condensate in an ultra-cold atomic gas, turning a 70-year-old theory into visible quantum reality. Along with Eric Cornell and Wolfgang Ketterle, this pioneering work opened a whole new field of ultra-cold quantum gas research. His groundbreaking work gave physicists an entirely new state of matter to explore, where millions of atoms behave as a single quantum wave. This has opened the door to new approaches in precision measurements, advanced atomic clocks, quantum simulation, ultra-sensitive quantum sensors, and emerging quantum technologies. In this special lecture, Professor Wieman will discuss how research on learning and classroom experiments are revealing more effective ways to teach and evaluate science and engineering, shaping a modern approach to science education for the 21st century.
We warmly welcome you to this special Nobel Laureate lecture by Professor Carl Wieman, organized by the Bhaktivedanta Institute, Kolkata. Thank you for joining us today as we explore the frontiers of modern physics and science education with one of its true pioneers.
Yeah, so that was a really interesting video. So now it's my great honor and privilege to invite the president of Bhaktivedanta Institute, Sri Vasudev Raoji, to deliver the welcome address for this event. Sir, please.
Hello, am I audible?
Sir.
Namaskar, good morning. Honorable Professor Carl E. Wieman, Nobel Laureate in Chemistry, and today's speaker, distinguished teachers, scholars, and students. Science, engineering, and technology have played pioneering role in shaping the advancement of human civilization. Advancement in the research of basic sciences is crucial for the advancement of science technology. Many times, advancements in engineering and technology necessitate breakthroughs in basic sciences research. Similarly, scientific breakthroughs require advancement in engineering and technology through sophisticated instrumentation and experimental design. A nation's progress and sometimes even survival depends on advancement, adaptation, and implementation of science, engineering, and technology. India, with a population of 1.4 billion people, needs support of science and technology to meet the basic needs as well as the aspirations of the young. India has achieved self-sufficiency in food grain production in terms of total output, thanks to advances in biosciences and technology. During recent COVID pandemic, India could produce its own vaccine and administer 2.2 billion doses of vaccines with the help of its Silicon Revolution and large-scale adaptation of mobile devices. In India, there are about 9,000 engineering colleges and 16,000 science colleges. However, a great effort is needed in science and engineering education to improve national research output and the employability of the graduates to satisfactory levels. We need to bring a fundamental change in the way students think and study science, engineering, and technology. It is exactly in this respect the genius of today's speaker, Professor Carl E. Wieman, a Nobel Prize winning physicist and educationist with a mission to bring fundamental change in the way science, engineering, and technological education is carried, is of immense value for us. Dr. T.D. Singh, the founding director of the Bhaktivedanta Institute, was always concerned with the quality education of students. He emphasized on the student-teacher relationship in shaping the student's career and life. I would like to bring his example in a simple way. During his PhD at the University of California, Irvine, under the guidance of Professor Tufts, he found unusual phenomenon of decrease in the rate of chemical reaction with increase in temperature. He thought something could be wrong. However, without twisting the results, he reported the same to his supervisor, who asked him to repeat the experiment. Same results were found, he again reported the same, and a new phenomenon was found, and that led to his PhD thesis. Therefore, a healthy and honest relationship between the teacher and student plays an important role in shaping the students, where the teacher provides an open atmosphere and assurance to students to feel comfortable to have answered wrong to the questions or report unusual experimental phenomena. And students remain sincere, hardworking, and honest to report unusual phenomenon because they could lead to groundbreaking innovations. We are delighted to share with you that the Bhaktivedanta Institute is celebrating 50 years of service to humanity. Bhaktivedanta Institute is unique in the sense that it was born out of open dialogues and intense debates between the wisdom of an old saint, Srila Prabhupada, and the scientific temper of a young, creative scientist, Dr. T.D. Singh, about the true nature of reality and life. With these few words, I welcome you all to the unique lecture on taking a scientific approach to science and engineering education by our distinguished speaker, Professor Carl E. Wieman, Nobel Laureate in Physics. Thank you all for joining today.
Yeah, thank you. Thank you, sir, for your insightful and warm welcome address. So before we begin the lecture, I would like to request all the participants to please scan the QR code displayed on the screen to submit your question to Professor Wieman. You can also take the screenshot or a picture of this QR code. And also the Google form link has been shared in the chat box. So please click on the link and type your questions there. You may submit your questions during the lecture, during the entire lecture, or after the lecture in the Q&A session. So now I would like to invite Dr. Sachidanand Rath, Associate Professor of Physics at IIT Bhubaneswar, to kindly introduce our esteemed speaker. Dr. Rath, please.
Good morning. A warm welcome to all of you to this meeting. On behalf of the Bhaktivedanta Institute, Kolkata, myself, Dr. Sachidanand Rath from IIT Bhubaneswar, is privileged to introduce the eminent speaker of the day, Professor Carl E. Wieman. So, Professor Wieman made history with his stunning success in producing the first ever Bose-Einstein condensate, a new form of matter that occurs a just few 100 billionth of the absolute zero. This discovery earned him and his colleagues a worldwide recognition. For this exceptional work, Professor Wieman was awarded the Nobel Prize in Physics in 2001, along with Eric Cornell and Wolfgang Ketterle. Experimental techniques and conceptual frameworks developed in his laboratory has become fundamental and contemporary research in quantum many-body physics, precise metrology, quantum simulation, and quantum information science. Professor Carl E. Wieman is currently Professor of Emeritus at both the Physics Department and Graduate School of Education at Stanford University, USA. His career represents a rare synthesis of fundamental experimental discovery in quantum physics and systematic evidence-based transformation of science education. Professor Wieman received his Bachelor of Science degree from Massachusetts Institute of Technology in 1973 and his doctorate in physics from Stanford University in 1977 with doctoral training in laser spectroscopy and atomic physics. Professor Wieman has played a central role in establishing physics education research as a rigorous data-driven scientific discipline. Over nearly 3 decades, he has conducted systematic investigations into student learning, conceptual understanding, and problem solving in physics, drawing upon methods from cognitive science and educational measurement. He founded the Physics Education Technology Interactive Simulation projects, which develops research-based interactive learning tools now used globally in physics, chemistry, biology, mathematics, and earth science across the globe. So the empirical studies associated with his work has demonstrated substantial and reproducible gain in student learning relative to traditional lecture-based instruction. Professor Wieman has also been a principal architect of large-scale institutional reform in undergraduate science education. Through science education initiative implemented at the University of Colorado and University of British Columbia, he led comprehensive effort to achieve department level sustainable transformation of teaching practices grounded in empirical evidence. This initiative provided a scalable method for integrating disciplinary expertise with educational scholarship and have influenced reform efforts internationally. His book, Improving How Universities Teach Science, published in 2017, offers a systematic analysis of these reforms and their broader implications for higher education. Professor Wieman's contributions have been recognized with numerous honors and distinctions. Besides the Nobel Prize in Physics, he was conferred the Laureate Medal, the National Science Foundation Distinguished Teaching Scholars Award, the Carnegie Foundation US Professor of the Year Award, the Oersted Medal of the American Association of Physics Teacher, and Wieman Prize in Education Research in 2020. He is a member of US National Academy of Sciences, where he served as chair of the Board of Science Education and is a fellow of multiple leading scientific societies. So with this brief introduction, I invite Professor Carl E. Wieman to deliver this lecture entitled Taking a Scientific Approach to Science and Engineering Education. Professor E. Carl E. Wieman.
Okay, thank you. I can see my screen now.
Yes, sir.
Okay, great. Yeah, so I'm going to talk to you about taking a scientific approach to science and engineering education. And first start out by saying that I don't see the goal as to turn all students into scientists, but I do see the importance of having scientific literacy for really every student, because this will allow them to make better decisions in their personal life, in their jobs, and in societal policies. So the goals of this talk are really for teachers to give you some perhaps new insights about teaching and how to do it better based on what we've learned in research. And for students, it's to give you an idea of what you need to do to learn more effectively. And also you can use this to sort of evaluate how good is the teaching you're getting. So I've organized this into start out with just a general introduction, something about how the brain learns complex thinking, and then focusing it down to talk about, to show you some applications of these ideas in university classrooms and measuring the results. And I'll just emphasize that almost all the research in this is from science and engineering, but there's good reason to think that the teaching approaches really are quite general, because they're really based on what we've seen about how the human brain learns. And then I'll go into more details about what some particular things research shows us about what improves learning and why. And then I'll finish with a brief comments about the role of AI in education, since that's something everybody is concerned about these days. So in the last few decades, there's really been new insights in how to learn and how to teach complex thinking like a good scientist or engineer. And it's come from three different areas that give us sort of complementary results. There's the cognitive science psychologists who primarily in the laboratory study basic processes about thinking and learning. There's the brain research. And then there's the work of people like myself who are, professors in physics, biology, chemistry, etc., who are actually doing studies and experiments in university science and engineering classrooms to find what works best. Now, the best data, and most of the data, comes from North American universities. And so this raises questions naturally about how sure are we that this applies to other countries, cultures like India and other grade levels. And what I'll say is we have general principles about how the brain learns that supports this, and some limited research at different levels in other countries but all say the same picture that argues that these ideas really apply quite widely both to different grade levels and other countries and cultures. So let me first start with sort of the most basic result, which is that is really rethinking how learning of this kind of complex thinking actually happens. And the old and still very pervasive model generally is that the student brains come into our classrooms and they vary in different ways. And then we immerse them in knowledge through the teaching and lectures. And that knowledge soaks into different amounts depending on the condition of the brain. And so with this model of learning, the focus is usually on selecting the best brains, giving exams and deciding who gets to come to university and who doesn't, etc. And then what to put in the knowledge soup, what topics to cover in what order, and so on. Now, although this model has been around for a long time and still very widely held, the research just says it's simply wrong, and that the research point of view shows that the brains, at least at the university level, aren't all that different, but they're quite changeable. And in fact, they're really transformed through the education process. The neurons are really rewired, hooked up in different ways as a result of the intense thinking involved in their education. And this rewired brain develops new capabilities. And you can even see this now with modern brain imaging. These are two the two brains of people who are in MRI machines and interpreting an X-ray image. And on the right is a medical student who's just learning how to do this. On the left is a radiologist who's very experienced and as an expert at this. And you see that their brains are activated in completely different ways, really as a result of the training that radiologist has. Now, one thing that this says really, which is very relevant to India, which I believe you have, you're one of many systems that have these very high stakes exams that determine what pathway a student can take, what schools they can get into. And this is a problem because these really, what my own group and others have seen is that these exams are really reflecting past educational opportunity or privilege of the student. They're really not very meaningful for predicting the future capabilities that a learner might have if they got a good educational experience. So one thing, just to say a little more about this concept, that the brain learns as it really, that it develops through practice. And, if you ask, why does this seem so strange? Well, I mean, if you think about a person who becomes a skilled musician or an athlete, and you ask, well, could they do that just by listening to someone tell them how to do it? And I think everyone would agree, no, that seems just silly. And so, that raises the question, why have people for so long believed that you can in fact become a skilled scientist or engineer just by listening to someone lecture about how to do it? And the explanation I have is that really the differences here are the levels of performance are much easier to measure in something like music or athletics. You can see when a person's, how good they are and how they're getting better. And so it's really, because of this, it's very obvious what teaching methods and how intense practice and coaching, what works best, because you can see just how they immediately transform into improving performance. But something like technical thinking, this is a very hard thing to measure, how well somebody can think about something. And so that's led to these wrong ideas about teaching for so long. But now recent research is really figuring out better ways of measuring how much students are really thinking and learning. And that's giving rise to showing better ways to teach, like I'm going to talk about in this in today. And so, the bottom line here is that the brain research is telling us that learning is really about enhancing the relevant neuron connections, and the brain primarily learns what it practices. It gets better at the thinking it practices. And so it's very much like muscle development. And this is really quite a new idea, that just like to develop a muscle, to make it bigger and stronger, the intensity and type of exercise that you do is really critical. That's equally true for the brain's development. And so, researchers like myself are continually seeking and learning new, more effective ways to learn and teach to help the brain more efficiently and effectively develop these new skills. Now, one of the important advances in this field is made by Anders Ericsson, who studied expertise across many, many different fields. And he's seen that this consistently requires a particular kind of practice. And in things like science and engineering, it's practice in the desired, the thinking that you want people to master. And so, but the requirements of this to be effective are, it has to be intense. The person has to really be putting fully focused mental effort into this. And that effort needs to be focused on improvement in what they're doing. And so you need to define very carefully what it is you want them to to become more skilled at. In this case, I would say thinking like a scientist or engineer really means solving problems, figuring things out. That's what they have to be focused on getting better at. And as well as just practicing doing this, they also then have to get feedback from a teacher on how to improve. And he's also shown that motivation is a really critical aspect of being successful at this, because this sort of serious learning is inherently hard work. It takes a great deal of mental effort. And so you have to be, the learner has to be motivated to put in that effort. And he's also shown that beyond the very beginning levels of any activity, unless you're looking at expertise, what really determines how good people are, how effective, skilled they are, is really how much of this high-level practice they've had. And that's really much more important than any other predictor, innate ability you might try and find for something. So it really says the educational quality is really the critical aspect of people's achievement. So this kind of practice tells you both what the learner needs to do and what the teacher needs to facilitate. And most of the rest of my talk is just going to be digging down into how this is actually done. And so I'm now going to switch to applying these basic ideas of this kind of what we call deliberate practice in university classrooms and showing you some results from this. I've done this transforming teaching to this form in now many six or eight different courses across science, engineering, and even medicine and medical training in different levels, and collected data on the improvements of the student outcomes with this teaching compared to more traditional lecture. So I'm going to go through some of that and give you a few examples of it. So this is learning in a large introductory physics class, where in the experiment, the class was large enough we could take two sections that were essentially identical student populations of 270 students each, and teach them in different ways and look at the learning they took away from class. And so the control section was taught by someone who was a highly experienced professor with good student ratings, but he taught a pretty basic standard lecture course of telling the students information, and while they listened, took notes. The experimental section was taught by someone who was a relatively new PhD, but trained in my programming these principles and methods of research-based teaching. And so these two instructors agreed to cover the same material in the same amount of time, and then both classes were tested on this right after they covered this material. So I assume you all are pretty familiar with what happens in the lecture class. Like I say, the teacher talks and the students listen. The experimental class was run rather differently. The students had a short reading assignment that just gave them some basic facts and terminology without taking up class time. And then during class, they would be answering questions. So this is an example where you have a light bulb and a battery here, and you close this switch, and then the students have to decide when that switch is closed, what's going to happen to the brightness of bulb number 2. And they've got different options. And then every student when this was done, they had a special device. Nowadays, everybody just uses their mobile phone. Every student has to answer this. And so when they answer, the instructor's computer records who the student was and what answer they chose, and can display to the instructor what the entire votes of all the class students in the class are. Now, once the students answer that, though, they're not told what the answer is. In fact, instead, what they're told is they have to discuss with their neighbors around them the reasons and why, and re-vote. And while they're having that discussion, the instructor isn't just standing waiting, they're circulating, listening in on those conversations, getting an idea of what's going on in the students' minds, what aspects of their thinking are like a physicist they want, and where they're confused and thinking about things incorrectly. After they then voted again, then the instructor demonstrates the answer, shows the results, and very importantly, then has a follow-up summary in which they provide feedback to the students on which of their reasoning and thinking was correct, and very importantly, what was incorrect and why, and so what they can do to change. That's where most of the learning actually takes place. Now, not everything can be done just on multiple choice questions like this. So on more mathematical topics, they would have to write solutions out on worksheets and so on. But so if you think what the students is going on in the students' brains during this, they're practicing thinking like physicists about this material. They're having to choose a conceptual model and apply it to this situation and see what it predicts. They're having to critique that reasoning of both themselves and their fellow students in those discussions. And so that's all kind of, the thinking that like a scientist does. But while they're doing that, they're also getting feedback from multiple sources to help improve their thinking. They're getting it from other students in the discussion. They're getting it by comparing what they predicted with what actually happened. And most importantly, they're getting it from now the informed instructor. Now, remember, this was an experiment. So there was given this surprise quiz given in both sections after the classes they'd covered in this material. And this was really measuring just the learning they got in class. The timing was such they weren't studying for exams or doing homework and so on during this period. So it was just looking at how much they learned from just coming to class. And here's the results where the test scores, the number of students on this axis and their test score on that axis. And you can see the experimental section scored much higher. In fact, on this particular test, random guessing would give a person about 3. So the amount to learn is really how far above 3 they are. And you realize from that, the learning from the lecture is really very small. And this matches with data we have from many other examples. But also I want to stress how you can see from these distributions that this isn't something that just helps the best students or just helps the weakest students. The entire distribution of the experimental class has moved up. So it's really better learning for all the student population. Now, here's a second example. This is done not by my own group, but by Beth Simon, who worked with me for a while. And they went and made the similar kind of changes in a different field. Now it was computer science. So they went to the 4 introductory computer science courses taught at University of California, San Diego. And there, the lecture, the same people but taught these courses, they just changed how they're teaching. And so they, in dark blue is the drop, and what they measured was also quite a different thing. They looked at the drop in failure rates from the students over the entire term of the course. And in dark blue are the numbers when they were just lecturing, and then they switched to this, what I call scientific teaching, but it's basically just what I described of asking students questions, having discussions in class. And the failure rates are now much lower across all of these different sections. So this is a case showing how you can have the same people, the same instructors, but they just adopt better teaching methods and they get much better results. In this case, they have about a third the failure rate they used to have when they were teaching differently. Now, most of this research is involved introductory courses because that's where large fraction of the students are. But my group and a few others have been looking at applying these ideas in more advanced courses, in particular undergraduate, more advanced physics courses. And we've shown that, and so those are smaller classes, they're much more mathematical, so the students are spending their time really filling out worksheets, showing calculations and so on. But again, they're working in small groups, having to answer questions while the instructor is monitoring how they're doing and giving regular feedback. And that's also shown to be a substantial improvement in student learning. And in fact, now the teaching of nearly all of the Stanford undergraduate physics courses has followed this form. Now, the structure of all of these courses is shown right here, and it gives you an idea of what the students and the instructors are doing, spending their time in class. So before class, the students have to do a little bit of preparation. The instructors think about what activities they want the students to have to work through to practice, and then introduce them for the day. And then the students work in their small groups, ideally 3 or 4 per group, on the activity while the instructor circulates around, listening to their discussions, looking at what they're doing, occasionally answering questions, but mostly monitoring the student thinking. And then at an appropriate point in the activity, typically after 10 or 15 minutes, then the instructor will pull the whole class together and give them feedback on how they're doing, giving the student perhaps new and additional knowledge that they may need, bringing all the students up to a similar level. And then the students return to the next section of the activity, and class just continues through this kind of cycle through until the time is up. Now, the 2 essential features here are that the students are thinking, they're practicing the scientific reasoning or engineering reasoning you want them to learn. And the instructors are much more knowledgeable about that thinking because they can see in real time, see and hear what students are doing. And so they can be much more targeted and effective in their teaching and feedback. So these are just a couple of examples. I've been able to tabulate something close to 1,000 research studies from across sciences and engineering that compare the traditional lecture with this, what we call research-based teaching. And the research-based teaching consistently shows greater learning and lower failure rates. Now, like I said at the beginning, we really only have data from science and engineering, but there's a lot of reason to believe that this applies really to all subjects. Okay, so I'm going to dig in now a little more detail about research on what works and how to improve teaching and learning and why. And this is sort of more targeted than just to the teachers. This diagram here sort of tries to represent a summary of a large body of education research. At the heart of it is at the center where the students are practicing solving problems. So learning to solve problems using the reasoning and knowledge of experts. And they're practicing with good feedback, where the feedback to be good has to be timely, specific, and actionable. Tell the students what they need to improve and they can actually do it. And across the top are the details of things that have to go into the design of the practice problems. Along the bottom is research goes into how to implement these in actual classrooms. And so I'm going to don't have time to go in detail, but I'm just going to touch on a few of these things here. But I'll just say that I think that this diagram, what it represents, really defines teaching expertise, and that it shows a set of practices that research shows if an instructor uses them, they'll consistently produce better learning. So let me start with the disciplinary expertise. This students really need to be practicing the thinking in the science that you want them to master. And this is a place where my own group's research, I think, provides important guidance, because we looked at a whole bunch, like 50 experts in science and engineering and a few in medicine, and how the process by which they solved authentic problems in their discipline. Because solving authentic novel problems is what scientists and engineers really do. That's what they're hired for, they get trained and paid for. And we found that across all of these people, their problem-solving process was defined by making a set of decisions that involved in problem solving. And we were able to identify 29 different decisions that they make in solving problems. What was really striking, though, is that almost every one of these people made these same decisions in their problem, in solving the problems. And so, if you're familiar with how different sciences and engineering are, you might think that sounds crazy until you look at what these decisions are. They're deciding, like, what concepts or mental models are relevant to the problem, deciding what information is needed to solve the problem, deciding how to find that information, deciding what approximations and simplifications are appropriate. Once you have information, deciding how credible is the information, what are appropriate conclusions you can make from it, and so on. And so once you see the nature of these decisions, you can realize, oh yeah, it makes sense that they would actually apply quite generally to different problems. Now, here's the full list of problem-solving decisions, and I'm not going to spend time going all the way through it, but there are different ones that involve figuring out the goals and the plans for for solving the problem, how to break it into pieces, deciding, as I said before, what information's needed, what calculations or analysis are needed. Once you have information, deciding how credible the information is, what conclusions are appropriate. And then there are these reflection decisions that I particularly want to stress, and that they're sort of the error correction decisions. They're the things where people reflect on and recognize when they don't have enough information or the method isn't working well, and so they've got to think about how to change it to be successful. Now, although the decisions are the same in all these different fields, the actual making of the decision is quite specialized, and it really requires specialized disciplinary knowledge relevant to that context. And so what we see is that experts have their knowledge organized around how it's used to make these decisions, why and how this knowledge is actually useful in solving problems. And so this has implications for teaching. It says that the most effective teaching is really providing the students, having them learn knowledge in the context of thinking how that knowledge is to be used, and particularly used in solving problems. So just to kind of summarize here, learning, I think the message is that to learn expert thinking, to learn how to solve problems at a level of a good scientist or engineer, means a student has to practice making these kind of problem-solving decisions in some kind of authentic context, practicing using the knowledge and reasoning of experts to do that. And to a large extent, that's what is usually meant when talking about critical thinking. So you can think about this as just also teaching students critical thinking. Now, I want to mention a couple of research studies we've done relevant to this. First, we did one where we compared we had two groups of learners, one in which they were practiced being told, here's a decision you have to make for solving this problem. The students had to then practice making that decision, versus the other group were told, here's a decision that's needed and here's what that decision should be. So that's really much more like most lectures approaches are done. And when we measured the students' ability to then make real useful problem-solving decisions in future problems, there was really an enormous difference with tremendous benefit of actually the actual practice making the decisions themselves. Now, the other point I want to make is that if you look at typical course and exam, textbook and exam problems, almost all the decisions that are needed for making solving real authentic problems are removed from the course problems. So, for example, students are given all the information they need, told what to assume. They usually know what concepts are important for that problem because it's a chapter 3 problem and so on. And so these are things that the way the problem is stated are taken away from the students. But these are absolutely essential elements of solving any real life problem you expect them to solve once they get out of school. So they're learning information, but not how to use it in a meaningful way. Okay, I'm going to quickly move on here to prior knowledge and experience and motivation. These are things where they both depend a lot and they vary with the students. And so prior knowledge is just the idea that you need to connect up and build on the learner's prior knowledge and experience. And so that means a suitable level of challenge to the practice problems you're giving. You want to be hard but not impossible, but that's very difficult because different students come in with different experiences, and so it's hard to make it optimum for all of them. Similarly, motivation is a really critical element. We know a little bit about enhancing motivation, picking some interesting or meaningful context for the material, why it's important and useful. It's also motivating for learners to believe they can learn the material and how to learn the material, and they get a sense of accomplishment in doing that. So these things are both important, but they both depend a lot on students' prior backgrounds, and they can vary a lot. And this variation makes one of the biggest teaching challenges of making this work for all broad distribution of students. Okay, I'm going to move on to talking something about brain constraints. This is something that's very well studied in cognitive psychology and not known in teaching at all, but it's really quite critical. And it has to do with how the memory works. Now, it turns out the memory has two components to it. There's the long-term memory, which is what most of us, when we hear the term memory, most of us think of. It has that very large capacity and very long duration. You can remember years, decades in the past, many different things. But in addition, there's something called the short-term working memory. This is kind of a buffer that information has to go through before it can get processed and into long-term memory. And the short-term working memory is very different from long-term. It's got a time scale of minutes that it sort of keeps track of things on. But more importantly, that it's got a tiny capacity that typical human brain has. A working memory can hold about 5 to 7 items at once. It's really how much you can pay attention to. But because of these limitations on the working memory, whenever the brain hears or the learner hears or sees some new item, it goes into working, that gets their attention, it goes into working memory, and that pushes out something that's already in there because there's not enough capacity. And so this has a lot of implications for teaching and learning. It means that any additional item that the learner is paying attention to is reducing the processing and learning of other things. And so you have to recognize that everything you tell students or have them work on, draw their attention to, has a cost in terms of learning. And so different elements of this, one of the worst offenders is split attention. If the student's checking their mobile phone or something in the computer during class, they're using up lots of working memory doing that. And so it's just a disaster for learning. And it's particularly bad because people are really poor at recognizing how big an effect it actually has. That's what the students can do, but there's many things the instructors do that put unnecessary demands on this working memory, and use of unfamiliar jargon, just covering way too many topics in a class than the brain can possibly keep track of, and absorb pretty pictures where they want to just make the picture look nice, so they add some details that get people's attention, but aren't critical for the information to be conveyed that asserts. And even the interesting little digression or jokes that actually hurts learning if it's not something that's critically connected with the material you want to learn. And this gets the biggest upset from both students and teachers, because the teachers will say, oh, but I tell the jokes, that's the only time the students are paying attention to me. And the students will say, that's the same thing. That's the only time I pay attention to them. It tells jokes. But the whole point is, if they're paying attention to the joke, they're not paying attention. They're not having working memory devoted to the learning that you actually want them to have. Okay, so I'm just going to finish up with giving a few comments about artificial intelligence, because that's something a lot of people think about these days, and then I'll take time for questions. So I see really there are two aspects of this question. The first is, what do we really need students to learn in the age of artificial intelligence, when they can get so much information from the AI? And the second is, in what ways do we think AI can actually perhaps help with education, teaching and learning? So the answer to the first question is really, I don't know. It's how do you best to use artificial intelligence to support authentic problem solving? At what level is it a useful support versus a sort of replacement for thinking and detrimental? And so, it's sort of what can be left to AI and what not. And although I don't know what the answer to that is, it seems to me the best way to find out will really be to just look at what successful scientists and engineers are doing in 10 years, how they're using artificial intelligence, and then use that as a guide for trying to teach students to use it in that way. But I am somewhat optimistic that there's some aspects of human reasoning that we're always going to need, and that is that for novel problems, that's the kind of things that scientists and engineers really spend most of their time on. You really still need human reasoning to make good problem-solving decisions when there's a lot of uncertainty, and by the problem being novel means there's a guarantee it's not in the training set the artificial intelligence has already had. So I think that's likely to be the kind of things that still are going to be useful for students. In terms of how it can help teaching and learning, this is something my own group has been researching for the last couple of years. And what we find is the hype is way beyond what the capabilities really are. And there's some major challenges to using AI as a teacher or a tutor. And the thing is, first, it's sometimes wrong, but worse than that is it's really designed around giving solutions, giving answers. That's not really very good teaching or effective feedback is effective feedback is really having a model of student thinking and helping the student correct their thinking and figure things out themselves. And so one has to work very hard to get around these sort of fundamental limitations of the AI. And so we've been making progress, but what we see is it really requires a whole lot of human intelligence that has to guide the AI to essentially give it some model of how student thinking and what the appropriate response to different kinds of student thinking to make it effective. And so I think like I say, we're making progress. It'll soon be able to assist with learning, but I think it's far from being able to eliminate the teacher because there's so much teacher wisdom that has to go into guiding an AI to be useful in education. Now, there's a different form of AI, though, that's different from the large language models that most people are looking at now, which has been shown to be clearly useful for education. That's these interactive computer simulations and this PhET project that I started a long time ago. It has a whole bunch of these across different sciences and math that are quite widely used. And these aren't large language models, but they are to artificial intelligence in the sense that the students act and does things with the simulation, and the simulation responds based on an algorithm. And so, and shows the students what happens. And so there is quite good data that on these helping learning. And the way they particularly help is it's just more effective ways to present scientific models, how to have students think about what factors are important and how they're related, that these kind of models guide most scientific thinking, and they help visualize the invisible, like behavior of electrons and atoms, and help the learner think about these things in the same way a trained scientist would do. And so here's a quick example I'll just show you of the circuit construction kit, where there's all these different components here. The learner can put together these components to make any circuit they want. I'm just an example of quite a simple one, figuring out how to make a light bulb light up, and then there's different things changing the voltage of the battery, and that makes the electrons move faster and the battery gets brighter, and they can make more complicated circuits and so on. But that just gives you a quick example of the capabilities of these things. And I sort of stress them here because they are freely available in many languages, and they are quite useful for teaching. So I'll just finish up here with, I think that research is really showing us good design and implementation for better education, giving better learning than what has been obtained with traditional lecture. And we really understand why those things work. And it has to do with really how the brain learns and functions, how it learns what it practices and develops new capabilities. Here's a bunch of references, and I'll somehow make my slides so that people can check these out if they want. Now, there's time for questions, but I'll start with actually one question that I often get, or I know that many people think about after this talk, is it's people ask something to the effect of, well, I say how bad lectures are, but they can't be that bad because look at all us university professors who were trained by traditional lectures. And my response to that is that, bloodletting was the medical treatment of choice, particularly in the Western world, for 2,000 years, based on exactly the same logic. And it was really only when medicine figured out how to do science and do proper comparison groups that they could see that actually there were better ways to do medicine than bloodletting. And so in my answer to this is, if you had a comparison group, those professors could have perhaps been even more successful than they are now. So with that, I'll stop and open the floor to questions.
Yeah, thank you, Professor Rani, for a brilliant lecture. And I would like to express my sincere gratitude to you for sharing such profound insights and for enriching us with your work on science education and highlight factors as well as challenges affecting the learning and teaching process. So now I would like to invite Dr. Dipankar Sharma, who has joined us from University of Basel, Switzerland, to moderate the question answer session. He will be presenting questions received from our live participants. So just a gentle reminder for the participants to also, you can see the bar QR code on the screen. So just scan it and put your questions. Thank you.
Thank you, Dr. Roshan. Thank you so much, Professor Carl, for such a wonderful session and giving insights into your teaching. Let me start with a question from Aniruddha Chakraborty. So I think it's from rather the last part of your talk, which talks about AI. So the question says, with the rise of generative AI, how does the scientific approach to education need to evolve to ensure students are still developing core critical thinking skills rather than just outsourcing the active part of the learning to machines?
So this is not an easy question to answer, but I would say there are certain things we can say about it, which is that, if you think about just asking students for questions with simple answers and numerical, what's a numerical answer to something, then AI can do all those things probably very readily. And so, that's not very useful. So I think what it really means is that you have to have students both practicing the thinking, the making these problem-solving decisions and how to justify them, what's a good decision. And so their answers, the activities and answers have to be more complicated than the sort of traditional simple number. They've got to reflect the actual thinking of the students beyond getting a right or wrong answer. And that I think that's and similarly they have to, in the learning, that's what they have to practice doing as well.
Yes, thank you so much. The next question, if Jagdish can share, is from Samiksha, and she says, my physics professor recently recommended PhET Interactive Simulations, and later I found out that you are the one who developed this. So she's asking, when and how did this come to you? And you thought about doing something like this. What inspired you?
So what inspired me is actually somebody else showed me the value of these things. It was developing another website, but there was a programmer who worked with me, and it was actually having to do with my work on Bose-Einstein condensation, where he developed some simulations to illustrate the physics of what we were doing and how we were making Bose-Einstein condensates. And I used them in my lectures on Bose-Einstein condensation, and I found two things. One is that was the thing that people particularly remembered what I was talking about, but also they seem to be effective and useful for an enormously wide range of audiences, from middle school students up to physics professors. And that made me realize that there's no other kind of educational material that has that kind of span of its usefulness. And so that inspired me to, when I got some money and opportunity, to start realizing I could go well beyond just showing my research and start using them for all kinds of teaching.
Wonderful, and thank you for that. It brings a lot of values to everyone. Yes, so the next question is from Yenugu Nikhil, and it's a little bit from your presentation when you showed the curve for performance versus test scores, he says that the curve seems to skew in the scientific teaching. So why is that so?
Hey, that's very observant, actually. If you look at it's sort of cut off at the top, but it drops
Exactly.
in a funny way. And there's a funny reason for that, which is that in the experimental class, it didn't actually cover all the topics. There was one of the topics that was supposed to be covered and was on the exam, and they didn't have time to cover it. So you see rather than all piling up at the top, there's a sudden drop off right at the end. It's worth noting that on that particular question, even though the students didn't cover it in the experimental class, they still outperformed the lecture class on that question. So they did better, but they did significantly worse than they did on the other questions. And that's why it's a sudden drop off right at the end, as opposed to piling up at the top like you'd expect.
Yeah, yes, thank you for that. There was a question from Nikhil from ISER Kolkata. So thank you, Nikhil, for that question. So next we have a question from Shravan. He's asking a more thoughtful one. He says, what are the factors that influence skill development in addition to just practice? Because I think you mentioned about you can exercise the brain and practice. The observation is sometimes we see child prodigies with exceptional skills. So what helped them to achieve that?
So this person I mentioned who's done so much studies on expertise, Anders Ericsson, he actually started out by studying what makes child prodigies. And he's come to the conclusion, and he's written quite extensively on this, that he's found that child prodigies, they just have more this kind of rigorous practice at a much younger age. And he's gone and documented this in some detail, that they think of child prodigies as being exceptional, but the only thing that's exceptional really is their education. And and you can trace this back usually to their particularly unique parents and parental pressures, sometimes quite unreasonable, but so his work kind of raises the whole, causing to question the whole idea of child prodigies. And it's just simply people who have very intense practice at getting better at something at younger ages, much younger ages than most normal people. And that's what makes them stand out.
Okay, yeah, thank you. Thank you for sharing that. So the next question is from Aryan Neil, who's from Nicer Bhubaneswar. So the question is again related a little bit to the previous questions, like a follow-up. Is there such a thing as natural inclination, genetic effects on learning, or so such as he says theoretical physicist? Is it like gymnast that you have to start early, maybe when you have a natural ability?
Yeah,
something like that.
So this is a complicated question, and I think the honest answer is we don't know for sure. But what we do know is that innate ability is much less important for theoretical physics, etc., than it is for athletic performance. And I think I can give an explanation for this in terms of evolutionary biology, which is that, there's various physical characteristics. Some people are big, some are little, etc. All of these characteristics virtually always have some environmental conditions in which that physical difference is an advantage. If you're got a place where there's very little food, it's much better to be small. You don't starve to death as quickly as if you're big, and other conditions when there's lots of competition, being bigger is better. So all these things are kind of preserved in the gene pool because there are some conditions in which they are superior. I don't think there's any conditions in which being stupid is superior. And so I would argue that there's kind of much more or much less evolutionary pressure to be different in mental things as there are physical. And I think that explains why many of the tests show that there's not a great, great innate differences. It's really dominated by education matters.
Indeed, that makes sense. Thank you so much. So next question is from Yogesh Tambe, who is from Indian Institute of Technology in Bhubaneswar. And he asks, how thought experiments as being often done by scientists can help in teaching and learning process, and how to include them or inculcate that?
This is a good question and a good point. What we see we did this study of expert problem solvers, and they are busy. They're continually running mental thought experiments to guide the decisions that they make based on, running these thought experiments and predicting what's going to happen. And so what I think is we want to do students, we need to have students learn to practice doing that same thing and so, you can give them guidance about, all right, consider, this model for what would happen if the mass was much greater or much smaller, and how would it move, how would it change? And so that's having the students kind of apply the thinking of how to practice applying these mental models to predict what's going to happen. And I think that's just exactly what you need to do. You learn to do thought experiments by practicing them and in that way.
Yes, indeed.
But
thank you so much.
I do want to stress that it's a really great point, because we did see that this was such an important aspect of all of these skilled engineers and scientists were doing these thought experiments continually as they were working through the problems.
Yes. Thank you to Yogesh for bringing up that question. I would like to take a moment to just highlight that this event is also live telecasted in different institutes. Like I think you can see in NICER, it's being like telecast in IITs, the Indian Institute of Technology, the National Institute of Science Education Research. So we also have questions coming from them. So thank you all for whoever is telecasting and screening this in different institutes. So the next question is coming from National Institute of Technology, Calicut. The question is, can we model learning and cognition in biological brains in a quantum mechanical framework?
The answer is, I don't think so. I don't know very much about this, but from my understanding of these quantum mechanical models of consciousness, they are at this point kind of very vague and really not at all useful for modeling any reasonable thing that you can actually test them with. So, but that's way outside my expertise.
Indeed, I think they're in a very preliminary early stage of theoretical framework and so on. Yes,
Yeah,
I agree. Yeah, thank you. And the next question is coming from Shorasis Vishwas. The question is how to teach and learn, integrate and involve topics. So I think it's more like, the advanced topics like general relativity and QFT effectively in this approach.
So this is a useful question, because one area in which I didn't do directly, but I collaborated on a lot, was someone developing these approaches for teaching quantum field theory, actually, to advanced graduate students. And it turned out to be extremely successful. But, the idea was in some ways it's easier than teaching lower level classes, because at quantum field theory, you can think, okay, here's how a physicist is thinking. It's very immediate how they thought about this, the decisions they had to make in developing a quantum field theory and testing it, seeing it, and basically just have the student, this Peter Lepage is the one who is a pretty well-known theorist who did this but taught it very successfully. But he just thought, okay, here's the key decisions that one has to make in solving problems in this subject, and so presented those in simple enough examples that the students could actually have to practice making those decisions, see why they'd be certain things would work and other things wouldn't work. And so that was a good example that these ideas work very well, actually, at a very advanced course.
Yes, indeed. Yes, thank you. The next question is coming from Anas Imam, who is a student at Techno Main Salt Lake. So the question is, sir, there is a perception among critics and observers that modern physics has increasingly moved from being a strictly evidence-driven discipline towards layers of theories built upon earlier theoretical frameworks. So sometimes with limited direct experimental verification. So how do you view this concern, and what is your perspective on the claim that modern physics has lost its path?
So, I think what's behind this is presumably the attention to string theory, which gets a lot of attention in physics, but it's quite important to recognize it's really only still a pretty small part of physics. And so I think I and many other people are concerned about the attention and amount of attention and focus that string theory gets, in that it does seem to have gotten sort of lost the aspects of physics being an experimental science. And so, I think there is reason for some concern about that, but I think it is important to recognize that it's not all of physics. It's really only a relatively small part, and there's still lots of other kinds of physics that are doing just great and still firmly based on experiments like they've always been.
Yes, thank you so much for the answer. So next question is from Desika Lakshman. I do not have her institute name. She asks, what set of daily adaptations a student should make in order to learn or grasp better? So some sort of daily exercises, a daily routine.
Yeah, so I guess what I think of is they should first really think about how to focus their efforts. And so, that when they're going to work on learning something, they should make sure that that's their sole focus, is learning that material, not carrying on conversations with other students at the same time, not watching television, etc. That the learning, they should think of it as hard work that takes really focused, extended effort, that they put that time and effort into. The other thing I think that's useful to practice is what they say, reflection of, regularly getting in the habit of regularly thinking, okay, do I understand this? Am I learning it? Should I do something different? Can I do something different to learn it better, or to solve this problem better? These kind of reflective, just practicing doing that kind of reflection, I think it doesn't really help. People don't naturally do it, and so it helps to really think about actively practicing it. Also, it helps to actively practicing it with other people. I think the social interaction, there's some indication that social interaction sort of helps one dislodge, if you like, the errors in how you're thinking, and different helps you stimulate different ways of thinking on things. And so sometimes just having conversations in which you explore these ideas that you're trying to figure out would be a good daily practice as well.
Yes, indeed. Thank you so much. I think this helps a lot of students. We have a few hundred students joining from all over India, and I mean, such advices always helps everyone. Thank you so much. Next question is from National Institute of Science Education and Research, Bhubaneswar, from Sartatru. The question is, can you please give an example of how scientific teaching be applied to advanced courses? So this is again similar to what you addressed for QFT and general relativity earlier.
Yeah, and so I think for advanced courses, you're like I say, you kind of want to think about how physicists. I mean, when you're presenting new material, new physics knowledge, that's always knowledge that was produced as a way to solve a problem and as a way to help solve one of these problem-solving decisions that I talked about. And so that's kind of the general concept. Now, to give a specific example, I don't remember the ones for quantum field theory well enough. I remember one for a fourth year modern optics class, and where they have to think about different formalisms for treating polarization, and and then where physicists have when it's simple, you can treat it in one way, and then you get more complicated with systems with more complicated matrix formulations and so on. And so, there it's just a question of having students understand what the problem is and struggle with, okay, here's a problem I need to think of a way to solve. And then you can, after it turns out, it really helps have them think about it first, and then you provide them with the solution. Oh yeah, now I see how to use this. I see what it's used for, how I can solve that problem. So that was one example. Another was just thinking about interferometry and how you would treat an interferometer with loss, and so they'd first go through how to theoretically describe an interferometer, and then what would a loss term have to what would it have to look like to properly convey the behavior of loss at the mirrors, and how would the equations have to change, and they have to think how to do that, and they struggle with it. Some of them succeed, some of them don't. Then you give them feedback to help them all understand how they'd have to do it.
Yes. Thank you so much for the practical application. It explains and helps us understand. So the next question is from Rajesh, who is from Meta AI Technology, who I think he's himself a tutor also. Is asking if learning is a transformation of the brain rather than accumulation of knowledge, how should education systems move away from high-stakes exams towards assessing real cognitive and problem-solving capabilities?
Boy, that's. I wish I knew. It's hard to see how you're going to completely get away from some measures of learning mastery, and so that means thinking about what your exams are really asking and what you're testing, and that goes back to the questions about when you've got AI to give answers, what kind of questions could you ask? And so I think my same answer would there still apply, is you have to think about exams that probe much deeper in terms of the thinking rather than just getting answers. And and particularly, these high stakes and very large scale exams really tend to be very much focused on remembering information, remembering procedures, remembering equations to use, and simply remembering things rather than understanding in novel situations what to do is kind of more useful than simple memorization.
Yes, indeed. Yeah. So we have more questions. The next question is again from AI, is from Pandit R from Strive. He asked, if AI can support routine problem solving and feedback, where should educators draw the line between what AI should do and what must remain a human responsibility in teaching and learning?
Yeah, this is a really hard question to answer, and it's particularly hard because the technology is continually changing. The thing that we see that AI is really poor at is having a model for student thinking. And so, the most effective teaching is you understand how a student is thinking about something, and you help them improve their thinking. And AI is very bad at doing that. And so, like I say, our work, a lot of it is to try and show the AI, to give it some kind of crude tools of, when students say this kind of thing, that means what that means and how they might respond to it. But I think there's always going to be a place for a good teacher who can understand how students think and can work with their thinking. I mean, I just think AI is, as we see it, is a long, long ways from being able to have that kind of capability.
Yes, makes sense. Thank you so much.
But let me just add to that.
Please.
I mean,
yes, please.
What that stresses, though, is the importance of good teaching being things where the teacher really is figuring out, getting information about what the student is thinking. So when you're just lecturing to a bunch of students and just talking to them, people tell me they think they can read their faces and know how they're thinking, but I don't believe it, and our data never does it. Always shows it's not true, and so I think, this emphasizes the role of a teacher who's really listening to student discussions, seeing what students are actually doing, and so has a much better idea of what they're thinking. They can be much more effective that way.
So it's important to get feedback real time so that they can improve on that.
Exactly. Yeah.
Yes. Thank you. So, Dr. Carl, I think, the time-wise, we're on we reached the time, but we still have very nice questions. If you would like to answer a few of them, we could extend maybe 5-10 minutes. What do you think about that?
Yeah, I could go
Is that
10
okay
more
for you?
minutes, and then, yeah.
Okay, let's say we go 10 more minutes. Thank you so much. We have so many questions coming from all the participants. So the next question is coming from, yes.
I was just going to say, they're really good questions. That helps.
Yes, indeed. Yeah, thank you. Thanks to all the participants. So the question is, again, it's very interesting. The question from SRNK Government Degree College, Panswara, says, Mr. Binay Kumar says, how to handle the students who are emotionally weak in this approach?
Yeah, that I don't really know very well, to be honest. Our research doesn't touch on that very much. I mean, I know that having a teacher who's supportive and sort of shows they believe students can be successful, is very meaningful and important for students. But beyond that, I really can't offer any good advice. I just don't know enough about that particular aspect of teaching and learning.
That is also a little bit difficult to quantitatively formulate this emotional weakness and measure them, right? It's a little bit difficult. Yeah. Yes, thank you so much for that. The next question is from Dr. Raman Lal, who is an educator at Data ISER. If decades of cognitive science show that learning requires effortful thinking that reshapes the brain, why do our education system still rewards speed, correctness, and exam performance? And what does this reveal about what we truly value in education?
So, I mean, I think it, what I would say, it says that people are awfully slow to accept research and and act on it. I don't think there's much more to say about it. I spend my time trying to convince people to change, but it's a slow business. Realistically, the system's been in place for hundreds of years, and so people don't adapt very well. I'll say that, a large part of it is just sort of history and culture. It's the way things have been done, and people don't like to change very their belief system and their actions very readily, and so that just makes it hard.
Definitely, I cannot agree more to that point. The change is difficult. Thank you so much. The next question is coming from Yosuju Naveen, who is a BSMS student at ISER Kolkata, Indian Institute of Science, Education and Research, Kolkata. So the question is, you identify motivation as a driver for long-term memory. In your research, have you found that intrinsic motivation, like a deep curiosity or a sense of duty, leads to more robust expert-making decisions than extrinsic motivation, like grades or career status? So talking about intrinsic and extrinsic, yeah.
Yeah, and so this hasn't been a field that I've particularly studied, but I'm aware of people who have and what their results. And intrinsic motivation is always better, and it's just fundamentally better for learning than extrinsic. And one of the drawbacks, with extrinsic things like grades and so on, is they've shown is that once the extrinsic motivation is taken away, people just stop doing that. Even things where they previously had intrinsic motivation, they liked doing something, when they had the extrinsic and then the extrinsic was stopped, they stopped doing the activity, the learning, whatever. So intrinsic sort of lasts better and is more effective and more useful always than extrinsic. But we live in a system I when I work with teachers, I explain to them that you really can't expect students to not be paying much more attention to the extrinsic motivation, because they were conditioned to that, that they go through a system in which that's all that mattered. And so you can't expect them to be looking for intrinsic reward motivation to learning, and to ignore grades and extrinsic things, because the system is just so highly conditioned on that way of thinking for them. So in teaching, I think you have to sort of do your best to nurture. You have to live with extrinsic motivation and extrinsic measures, because that's kind of a expectation, a requirement, but you have to do your best to still instill the intrinsic motivation in students.
Yes, indeed. Also true for other fields where it's sustainable and works better. Thank you so much for insight. So next question from Bhavini, who is from Birla Institute of Technology and Science from Pilani. The question is, what made you stand out? What are the 3 skills you would recommend budding scientists to develop in order to reach such great heights as yours?
So, I think I'm a good example of, in some sense, of what I've said here, which is that I was not a child prodigy or anything close to it. I was okay, but not great in school. I did lousy in my first university physics course. The thing that I was unique at is I was very focused and I worked very intently and very hard. And, so this business of intense focus effort, I see as almost entirely, what made me successful. There were many people who were, when I was younger and in college, more successful than I, but over time, I just worked more than they did and learned more eventually and became more successful. So I think it was, now at some level I had more motivation and that helped. And that's partly my personality and partly the area I got involved in was a good fit to what I wanted to do. But, I think that was the main thing that made me successful.
Yes, and I hope that was intrinsic motivation coming from you.
It was, no question. Yeah.
Yes, thank you so much for sharing that with us. Next, we have a question from Snehil, University of Petroleum and Energy Studies, Dehradun. The question is, we know that geniuses exist who excel in certain fields without putting in excess work or extra effort. So again, it's in the similar line as we discussed before. So is it possible for people born without those special genetics to increase their insight and reach that level of fundamental intellect through effort alone?
Yeah. So first, I disagree with the claim made at the beginning that some people are, can become such great without putting in much effort. I think this again is something that this Anders Ericsson has studied quite a lot, and of looking at high-level experts across many fields, and he finds they always have to put in lots of effort. There are some who like to pretend that they don't put in effort to sort of try and convey that they have some sort of unique genius, but they actually are hiding. They really are just pretend, like they say, it's pretending. And when you look in more detail, you find out, no, they actually did lots of hard work to reach their level of success.
Yes. Thank you so much. I think my 10 minutes are over, although I would like to keep going, but with regard to time and everyone here. So thank you so much, Dr. Carl Wieman, for your wonderful interaction. I think it was very nice the way you addressed all the questions. I'm sure all of our participants got a lot of insights and something they can take here from today, which would help them. So before we finish, a few things I'd like to request everyone to please turn on your video so that we can take a group screenshot. I mean, a group photo we cannot do like in real life, but we can do a screenshot where everyone can turn on their video. And I would like to ask our volunteers to please click as many screenshots as possible so that we have a memory of all of us being together today, enjoying this beautiful lecture. And, so we will wait for a while so that more and more of the participants will turn on their video so that we can make the screenshot. Thank you all. I see many people turning on. Sometimes it takes a few minutes for everyone to come to the video. But we can already start taking pictures. The volunteers, I'd like to request them. And yes, so I mean, we are still, I think I still see people turning the videos on, coming. So we had a few of us already dropped now, but I would like to request all of you to stay. We have vote of things and a few announcements later on. So please stay tuned for next maybe 5 to 10 minutes. I wouldn't take more than that. so that we go through that. And it's nice to see all of you joining from different parts of the country. And thank you so much. Please keep turning your video on if you haven't done it yet. I think I'll take 2 more minutes so that everyone, whoever missed, can also come and join us. And I hope the pictures are being taken. Okay, thank you. I see more people turning up. Okay, I mean, it's a little bit different setting, so I mean, we don't have a cameraman in front who would make us smile, but please try to smile so that we get nice pictures from all of you. And yeah, thank you all for turning your video on. Okay, so I think let me share. I think thank you so much once again for turning the video on to make this group photo. I think we will proceed now with our vote of thanks and some announcements. So please be with us for next 5 to 8 minutes. So now I would like to request Dr. Sunil Kumar, who is a principal scientist and head at Animal Biochemistry at ICAR, National Dairy Research Institute, Karnal, to deliver vote of thanks for this event today.
Thank you. A very warm greetings to everyone. It's truly an honor to deliver the vote of thanks for this remarkable occasion. To begin with, I would like to extend my heartfelt thanks. I would like to extend my heartfelt gratitude to our distinguished speaker, Professor Carl E. Wieman, Nobel Laureate in Physics, who is a visionary in revolutionizing how we think about teaching and learning. Despite his demanding commitments, he generously accepted our invitation and joined us virtually and enriching us with his profound insights on taking a scientific approach to education. Let us all extend a heartfelt round of applause to Professor Wieman. So, Professor Wieman, your lecture was really extraordinary. It clearly showed how the same careful approach we use in scientific research can also be applied to improve and transform science and engineering education. Your groundbreaking work, from the creation of the Bose-Einstein condense to your pioneering research in discipline-based education, demonstrates that learning is not just about the transfer of information, but actually to develop an expert-like thinking. Through your insights, we have come to appreciate how data-driven teaching methods can unlock the potential of every student. Personally, I found your talk is very inspiring as it demonstrated that the quest for truth in the classroom is just as vital as the quest for truth in the laboratory. Scientific inquiry, as you beautifully articulated, is not just a subject to be learned, but a mindset that empowers us to solve the complex challenges of life, including in physics and other subjects too. Your dedication to improving how we share knowledge reflects a deep commitment to the betterment of humanity. Once again, let us give a warm round of applause to Professor Carl Wieman. Now, in today's fast evolving world of technology, it is truly inspiring to witness individuals and institutions dedicated to fostering meaningful dialogue and the pursuit of knowledge. I am deeply appreciative of the collective effort from all the organizations that contributed to ensuring this lecture reached a diverse and engaged audience. I am particularly grateful to our knowledge partners, Dr. T.D. Singh's Quest Club, IISc Bangalore, Jignasa, Science Consciousness and Inner Quest Group, IIT Bhubaneswar, SOA University, Bhubaneswar, NRI Group of Institutes, Agiripalli, Vijayawada, Government PG College, Ranikhet, and Aditya Degree College, Padamata Lanka, Vijayawada, PB Siddhartha College of Arts and Science, Vijayawada, School of Planning and Architecture, Vijayawada. Their unwavering support ensured that we reached a wide and diverse group of students and professionals. I would also like to thank CSIR Labs, IIT Kanpur, IIT Guwahati, IIT BHU Varanasi, IIT Tirupati, IIT Dharwad, Baba Atomic Research Center, BITS Pilani, ISER Mohali, NISER Bhubaneswar, NIT Warangal, and many other academic institutions for promoting this lecture within their campuses and encouraging active participation from students and professionals alike. On behalf of the Bhaktivedanta Institute, I sincerely thank the directors and management of these institutions for their invaluable cooperation. The success of any event lies in the energy and engagement of its participants, and today it has been no exception. I sincerely thank every attendee for their active involvement, thought-provoking questions, and unwavering attention throughout the session. Your contributions have truly elevated this event into a memorable and impactful experience. Behind every successful event lies immense effort and meticulous coordination. I would like to acknowledge the incredible contributions of our student volunteers who worked tirelessly behind the scenes, from designing posters to ensuring a seamless execution of the program. Their dedication has been key to the event success, and I extend my heartfelt thanks to each of them. Lastly, I express my deep appreciation to Srila A.C. Bhaktivedanta Swami, the visionary founder Acharya of the Bhaktivedanta Institute, and Dr. T.D. Singh, the founding director, whose groundbreaking efforts in fostering a science-spirituality dialogue have brought all of us together today. I am also grateful to the Almighty for providing this platform and guiding us towards organizing more impactful events like this. As the Bhaktivedanta Institute celebrates 50 years of its dedicated service, I would like to thank all its members, past and present, who have contributed to initiatives such as the World Science Congress, AISSQ, Summer and Winter Schools, publications, Bhima, essay competitions, seminars, symposiums, and lectures. To conclude, I thank everyone who made this lecture and as an enriching experience. I look forward to seeing you at future events. Thank you once again and have a great day.
Thank you so much, Dr. Sunil, for delivering the vote of thanks. Once again, thank you, Dr. Carl Wieman, for being with us. It was really my pleasure to talk to you, to interact with you. It was a wonderful interaction. Thank you, Roshan, for letting me do that. So I will continue with introducing or showing you a few publications from the Bhaktivedanta Institute, give you a glimpse of it so that if it interests you, then you could approach to read it. So there's this quantum physics and consciousness conference that was held, and then we have this article booklet which has articles from Nobel Laureate in physics like Eugen Wigner, Anthony Leggett. It offers a rare and intimate glimpse into the foundational thoughts of the giants of 20th century science, like Max Planck, Niels Bohr, and Werner Heisenberg. This collection focuses on the fascinating moment in history when the discovery of quantum mechanics began to shape our understanding of the physical world, exploring how these Nobel laureates, Wigner and Leggett, navigated the profound scientific implications of their own revolutionary research. So you're most welcome to discover understand this, you can by visiting store.beans.org, and also many more collections there. One more interesting thing is this Savigyanam, which is a journal from Bhaktivedanta Institute. Astonishing breakthroughs in the precision of atomic clocks and intricate mechanics of laser cooling awaits you within the pages of this latest volume. Remarkable developments in the study of DNA and nucleotides are expertly explored alongside the profound foundational principles of quantum measurement, cosmology, and complexity of biological evolution. So it's a privilege to introduce a work that so elegantly documents these fascinating milestones of modern scientific inquiry. It also includes articles by Nobel laureate William D. Phillips and Charles Townes. Please, you can explore this, read this by availing this journal from store.beans.org. One more very important, very interesting, one of my favorite publications from Bhaktivedanta Institute is Science, Spirituality, and Nature of Reality, which is a dialogue between the two pioneers, Sir Roger Penrose, who is Nobel laureate in physics, Dr. T.D. Singh, director of Bhaktivedanta Institute. They explore the vastness of cosmology and beauty of mathematics, insights into space-time, and the quest for quantum theory of gravity, and the brilliant exchange of ideas in this book. So please visit the store and try to explore and read and go through this publication. One more very, very, very interesting and interactive publication is this consciousness book, which gives a breathtaking inquiries into the neurobiological substrates of life and the quantum decoherence. In this remarkable study in this book, extraordinary perspectives on molecular biology and non-local phenomena are presented with deep appreciation for the rigorous pursuit of empirical knowledge. So this compelling work, along with further research into the scientific frontiers, is accessible and again store.beans.org. So please visit the store, and you can really find many more books and publications and articles there. A very important announcement is that we have this upcoming lecture series, Golden Jubilee Lectures on the Voyage to the Cosmos. Starts March 16 to 22. It's again online, like this one, organized by Bhaktivedanta Institute. Please take a screenshot or note down the numbers and the address so that you can really go into this and learn more about it. We have topics like looking into the universe, new frontiers and introduction to space equipments, space-time and the human mind, and exploring the quantum theories of the universe, Big Bang, string theory, and many more. We have speakers from all over the world. As you can see, some of them are displayed here. Andre de Linde, who's from Stanford University. We have theoretical physicist John Swartz from Caltech. We have Timothy Eastman from University of Alaska, Mario Livio from Space Telescope Science Institute, Maryland. So we have wonderful speakers and many more who would come present their thoughts and their research on these topics, on various topics which are mentioned there. So please, you can scan or take a screenshot of and visit the page to register